All right. So, apologize. This week's been crazy. I don't have the test yet. I would like to say I'll have them tonight. It'll probably be sometime tomorrow. I'll post them on Canvas, and so you can have the scores as soon as I get them done. So far, it's looking like like I would expect. Okay? There's about 7 or 8 that are awesome. About 7 or 8 that are somewhere in the middle, and then about 7 or 8 that were struggling a little bit. It's pretty normal. I don't know, maybe. But I'm not done with them. So sometimes if people do really good on like the first part, then they struggle on the second part. And so we'll see. But they're not like unusual or anything. Okay. All right. So my voice is giving me a really hard time right now. It sounds good to me. I mean, as good as it gets. Okay, just about. Like basically all morning, I've barely been able to talk at all. Okay. So I'm shifting our plans a little bit. Okay. Let's look at the calendar here. Okay. So the plan was I had to work on 4.3 today and Friday. And then we've got spring break. And then after that, we would only have one more section. We would review on the 30th and then take test 3 on April Fool's Day. So I think what we're going to do is so what I was going to do is we were going to look at this stuff in 4.3 and look at a bunch of examples as we went along. So I think instead, and it'll make everybody happy probably anyway, I think instead what we're going to do is we're basically going to look at all the material, and then I'll make you a video when my voice gets better with a whole bunch of examples doing all this stuff. Okay? So Friday will be a virtual day. Okay? It'll be a virtual day. All right? So whoever's been praying I won't be able to talk so we can get our class Friday, quit. All right, we're out. So, we're out. But and then the assignment for 4.3 is not due until the 25th, right? It won't, as I haven't only had it posted yet, but it won't be due until the week after, the Friday after spring break. So that's going to put us on that Monday. If we need to do some more stuff from 4.3 together, we can. Okay. So that'll put test 3 either on the 1st or the 4th, depending on what we do on that Monday. Okay. And then, just while we're talking about it, the 27th last day of classes, so that'll put us on target to have test 4 on the 22nd. And then the 25th and 27th, we can just spend on getting ready for the final. Okay, so basically 2 review days that last week. Okay.
Is there a date set for the final?
Yeah, it's let's see. I forget what it is. We can look. Find the right folder here. Open. Well, did not put it on here? Okay, hang on. I usually put it on the syllabus, I guess I did. So let's look at the final exam schedule then. Come on. We made it Monday Monday, Wednesday, Friday at 1:45, so we'll be May the 2nd from 1:30 to 3:30. Okay. That's Monday. Yeah, almost, yeah. Yep. Sorry, I didn't have that on the syllabus, so you should put it on there. All right. Questions on schedule we got coming up? Nothing? Is it okay with everybody if we do a virtual day Friday? So that way, if I still can't talk Friday, I can wait and do the video Monday or something like that, and just have it out there whenever. Okay. So, all right. So let's take a look at section 4.3 then. Okay. So our big objective in this section is to think about if we have a function, we're thinking about the graph of a function, how does the derivative come into play there? What kind of things does the derivative influence on the graph of a function? And we're also going to look at the second derivative a little as well. Okay. So start looking at the derivative. So think about this with me. So if we're looking at this graph, okay, and we've got these little pink tangent lines in there that are maybe a little hard to see on here, but here we've got a tangent line with a positive slope, tangent line with a positive slope, tangent line with a positive slope, and then when we go over the hill, what changes? Our tangent line, what changes on the slope? It goes negative, and then goes negative, and then when we go past the valley, it goes back positive, positive. Okay. So that pattern is meaningful. Okay. So what we can say where we have a positive slope, like between A and B on this graph, okay, we can say that our graph is increasing, or that our function is increasing between A and B. Okay. And that kind of makes sense if you just, intuitively think about it. Our y values are getting bigger, right? As we go along the interval from A to B, our y values get bigger. And then between B and C, our y values start getting smaller. So we could say between B and C that our function, or that our graph, is decreasing. And then again, starting at C, our y values are getting bigger again. Okay, so we can say between C and D, our function is increasing again. Okay. And our first goal is just to relate that to what's happening with the derivative. Okay. So we said between A and B, our function is increasing. Okay. What's going on with our derivative between A and B? Our slope of our tangent lines. They've all got something in common. The graph's increasing, and the slope of all these tangent lines, what they have in common, they're all positive. They're all positive. Okay. Our function is decreasing between B and C. Got a couple tangent lines in there. What's going on with those? Have negative slope, a negative tangent. Negative derivative, sorry. And then again, where we're increasing, positive derivative. Positive derivative. So that's our first little tool here. Okay, you can prove it with the mean value theorem. We won't, thank goodness. Okay, but you can. That says that on an interval where our derivative is positive, that means our function is increasing on that same interval. Okay. Or if our derivative is negative, that means our function is decreasing on that interval. Okay. You can have a mix of both, right? We have some intervals where our function's increasing positive derivative, and then some intervals where our function is decreasing with a negative derivative. You can have a mix. What we want to be able to do is we want to be able to take a function and then figure out where it's increasing and where it's decreasing. Like what intervals over what intervals is this function increasing on, and then over what intervals is this function decreasing on. Okay. So what we've got to figure out, when our derivative is positive, when our derivative is negative. Okay, to do that, we've got two inequalities we're working with. To do that, how we can start off is by finding where our derivative is 0. Okay, our derivative is 0. Okay, so here's a function. They factored this one to solve because it was cubic, and that was really the only good option. If you have a quadratic, you can use any method to solve it. For 0, it's no big deal there. You don't necessarily have to factor, is what I'm saying. But here they took the function, found the derivative, okay, and then factored the derivative. And then we want to find where our derivative would be 0. So we just set each factor equal to 0. So if x is 0, we make our derivative 0. If x is 2, we'd make our derivative 0. Or if x is -1, we'd make our derivative 0. Okay with that part? Just solving an equation. Okay. And then, that's the hard part. Okay. Then we can just make a little number line. Our textbook makes a table. I think that's more work than it's worth. I've always just done it with a number line. Okay. And then we put the places where our function is 0 on the number line. Okay. We also need to check to see if there's anywhere that our derivative does not exist. If there's anywhere our derivative is undefined. Okay. What we're doing, we're finding the critical numbers that we talked about last time. Okay. So a shorter way of saying what we're doing is find the derivative, find the critical numbers of the derivative, okay, and then plot those critical numbers on a number line. Okay. And then all we have to do, okay, is we just pick a test point from each piece of our number line. We've got this split into four intervals, right, where we've got it cut by the places where our derivative is 0. Okay. So then we just pick a test point out of each one of those intervals and figure out if our derivative would be positive or negative on those. Okay. So let's just do this one. Let's get some scratch paper here. I feel like I'm making it sound more complicated than it is. So on that example, well, here was our function we started with. Okay. If we take the derivative, we get 12x cubed minus 12x squared minus 24x. Okay. And then we could factor that. Actually, they've already given it to us in factored form, so we'll cheat, use their factors. And if we take each one of these factors, set them equal to 0, we'll get a solution that'll tell us where our derivative will be 0. Okay, what x values will make our derivative 0. So 12x will be 0 when x is 0. X minus 2 will be 0 when x is 2. And then x plus 1 will be 0 when x is negative 1. Now what do we pick test values out of each interval? Plug them in. If you've got it factored, you can plug it in there, or you can plug it back into what you started with the derivative. And we just want to check the sign. We just want to know, is our derivative positive or negative there? So we need some test point from this first part of our number line. So we need some x value that's smaller than negative 1. Pick anything that works. I think try to pick something easy. Negative 2, I think, is a good test point. Okay. So if we plug in negative 2, we're finding f prime of negative 2. And we don't even really care what the answer is, we just care what the sign is. Okay. So since we've already got it in factored form, we can just think about plugging in negative 2 and figure out what the sign of each factor would be. And then that'll tell us what the sign of the derivative would be. Just being kind of lazy about it. Efficient is probably a better term there. Okay. So if we plug in negative 2, we'll have 12 times negative 2. Will that be positive or negative? Negative. And then we'll have negative 2 minus 2. Will that be positive or negative? Negative would be negative 4. And then negative 2 plus 1, that would be negative. And a negative times a negative times a negative is negative. Yeah. So negative times a negative is positive. Positive times a negative would be negative. So on this portion of our number line, get my pen adjusted here. On this portion of our number line, sign of our derivative is negative. I know it's negative on that whole portion by just doing that one test point, because the only way it could change is if somewhere in there it was 0, right? If you change from negative to positive, you've got to go through 0. So that's why we found the places where our sign could potentially change. That's where our derivative is 0. We're not guaranteed the sign changes, but if the sign changes, it can only change at negative 1, 0, and 2 on this one. So then we need a test point between negative 1 and 0. What do you want to use? Negative 0.5, negative 1/2. Okay. So we'll find f of negative 1/2 or negative 0.5. You can just take and plug it in the calculator. Either hit that there or there. Okay. Usually it's a little quicker just to check the signs like we're doing, but you could just plug it in. Nothing wrong with that. Okay. So here, if we do 12 times negative 1/2, is that going to be positive or negative? Negative. If we do negative 0.5 minus 2, that's still negative. And if we do negative 0.5 plus 1, that's going to be positive. Yeah, it'll be positive 0.5. So there we got a negative times a negative will give us a positive, and then times a positive. So we'll have positive sign for our derivative in that region. Okay. Two more to do. Same idea though. We need something between 0 and 2. 1's a nice easy value. Okay, so we'll find this is f prime, sorry, f prime of 1. Hey, we just care about the sign, so 12 times 1, positive. 1 minus 2 would be negative. 1 plus 1 would be positive. So the whole thing is negative. Negative. So sign of our derivative between 0 and 2, negative. And then we need one more, we'll be done. Need something bigger than 2. 3 is fine. Okay, so then we'll find f prime of 3, at least the sign. So 12 times 3, positive. 3 minus 2, that's positive. 3 plus 1, that's positive. They're all positive, so our derivative is positive. Okay. So then what we want to know, okay, we want to know where our function is increasing, where our function is decreasing, and that's something we'll write down in interval notation. So it's decreasing where our derivative is negative, and it's increasing where our derivative is positive. We've got 2 of each on this one. Okay, so our function is increasing on what intervals? Yeah, -1 to 0, and then 2 to infinity, that's right. Where we're increasing because those are the intervals where we have a positive derivative. I mean, their function's increasing there. Okay. And then we can do the same thing for decreasing. Okay, so where we're decreasing, -infinity to -1, and 0 to 2. 0 to 2. Okay. That's increasing, decreasing. Okay. The only thing that changes, well, we got a couple of things that change. Finding the derivative could be a little bit different. That one we got away with just using the power rule. Okay, so that could be a little more complicated. Then we would still want to find the values where our derivative would be equal 0, or where the derivative would not exist. We didn't have any of the does not exist values on this one. But once you find those, however many there are, okay, that could be any number, but however many there are, plot them on the number line. Pick a test point in each interval we've constructed. Check the sign of the derivative. That's it. The ones where we have a positive derivative, our function is increasing. The ones where we have a negative derivative, function is decreasing. Question there? Okay, so just remember, if we've got a positive derivative, that means our function is going up from left to right, so increasing. We have a negative derivative, means our function is going down from left to right, so decreasing. So let me show you what I'm talking about, how the textbook does a table. I get that here. It's nice and all, I just think it's too much work. So they take each factor and make a column for each factor on each interval. And then they keep track of the signs, and then they've got a column for the whole thing together. We're doing the same thing with just the number line. If you want to do it that way, you can. I don't think so. That's quite a bit of work to me. Okay. All right, and then here's a graph. Okay. So let's check ourselves. We said we should be decreasing from 0 to -1. Is that what we want? I don't have it marked here. And then increasing from -1 to 0. What was it? I forgot. Let's check ourselves. Yeah, we said we're decreasing from -infinity to -1. Okay, that looks right. Increasing from -1 to 0, so we're going up. That's right. Decreasing on 0 to 2. I'm assuming that's 2. No, 2. And then increasing on 2 to infinity. Looks right. Question on the idea there? Don't forget, I'm gonna make a bunch more. Give a bunch more examples in the video I make. Kind of got a little bit of a feel for the concept. Positive derivative increasing, negative derivative decreasing. All right. That's one thing we want to be able to check for. Number 2, okay, we want to be able to locate local extreme values, so local minima, local maxima. Okay. We've talked about local extreme values, okay, but like on our assignment, the only ones we had to find, at least algebraically, were absolute max, absolute min. If you have the graph, you already know how to find locals. Okay. But without the graph, we needed a little bit more information. Okay, so that's what we're looking at here. Okay. So, for figure 2 we're talking about. Yeah, here's back up. Okay. Looking at the graph here, okay, we should have a local minimum here. Was that -1, I think? And then a local minimum here at +2. And then a local maximum where? At 0. Yeah, local maximum there. Okay. So how can we tell that without seeing the graph? Okay. If we go back and we look at our signs of our derivative, okay, our derivative was decreasing, and then increasing, and then decreasing, and then increasing. Okay. If you think about the values where that change happens, our derivative is 0 there, or could possibly be a place where our derivative does not exist. So if you think back to last time, thinking about those things we call critical numbers, those are the only places where a local extreme value can occur. And so if we have a local extreme value, local minimum or local maximum, it can only occur when our derivative is 0. But we saw sometimes our derivative could be 0 and we don't have a local minimum or local maximum. How do we know which ones give us a local minimum or local maximum, which ones don't give us any kind of local extreme value? Got something called the first derivative test. Okay. So we can only have a local extreme value at a critical number, so either where the derivative equals 0 or where the derivative does not exist. Those are our critical numbers. And then we just look at what happens to the sign of our derivative on each side of those critical numbers. Okay. So if our derivative changes from positive to negative, okay, the local maximum. If our sign changes from negative to positive, we got a local minimum. And if we have a critical number with the same sign on both sides, so positive on both sides, negative on both sides, neither one is not a local extreme value. Okay. So to me, if you just remember we're talking about the slope of the tangent line, it's not too hard to remember which one's which. Because here we're changing from positive slope to negative slope on our tangent line. That means we're going up to start with, and then we're turning around and going down. So that's like a mountaintop or hilltop. So that's got to be a maximum. On B, if we change it from negative to positive, that means we're going down, decreasing, and we switch to increasing. So we've got to have like a valley there. So that's a local minimum. Okay. And then just remember, if the sign doesn't change, we don't have either one. Okay. So positive to negative, is a maximum. Negative to positive is a minimum. And then if it's the same on both sides, we don't have either one. So if we look at our little chart we made, we can see what we saw on the graph. Our derivative went from negative to positive at -1. So negative to positive, which one is that? Is that a minimum or maximum? The local minimum. Okay. And then our sign went from positive to negative at 0. Positive to negative, so that's a maximum. And then our sign went from negative to positive at 2. That's another local minimum. And that's what we saw in the graph. That's what we saw in the graph. On that one, we didn't have any interval where it had the same sign on both sides. Okay. We could have, but just that particular function, we didn't have that. Okay. And so here's another picture. Okay. And the same thing we talked about. Okay. To me, it's hard to just memorize the rule. And if you think about what that means, that we're changing sign with our derivative, it's easier to remember which one's which. So we remember what the graph looks like if we don't have either one. Be something like that. So here we got a critical number at C, but our function's increasing up until we get to C. We got a 0 derivative, but then it keeps on increasing after that. So positive derivative, 0, and then positive again. So there's no valley or hilltop there, so no max or min. This one's the same thing, just going the other direction where we're decreasing on both sides. Okay. Question there? Hanging in there? Okay. All right, so let's look at the second derivative a little bit. There's another example in here with sine. It's a little more calculation intensive, but we'll do some. I'll give you some more examples later. Okay. So sine of our derivative tells us where our function is increasing or decreasing, and where those signs change, we can figure out local minimums or local minima or local maxima. Okay. What about second derivative? So remember, the second derivative, if we're thinking about rates of change, our first derivative is the rate of change of f. Okay. So like the slope of the tangent line of f at every x value. So the second derivative is the rate of change of what? F prime. So it tells us how the derivative is changing. Okay? It tells us how the derivative is changing. So how does that relate to the graph? Well, here are two functions. First one, increasing on the interval from a to b. Okay? So positive slope on all the tangent lines between a and b. Second one, also increasing from a to b. Positive slope on all the tangent lines between a and b. But the two graphs don't look the same. They don't look the same. Okay. What's different? This first one's kind of like more like a bowl, right? Kind of curvature there. And then this next one's more like, I don't know, umbrella curvature there. Okay. So what we call that, okay, we call that the, let me see if the definition is next. Sort of. Okay, we call that the change, that difference in curvature between these two. We call the concavity. Okay. So if you think about science class, we've got concave and convex stuff. With functions, we don't talk about convex. We talk about either concave up or concave down. Okay. So this one, we'll get a better definition in a second. It's more precise. But this first one we would call concave up. Okay. And then the second one we would call concave down. Okay. One way, informal way to think about it. Okay, this one's concave up, so like if we had a whole shape that was concave up, you could think about like if it was raining, it would fill up with water. Okay, that's concave up. Concave down, if it rained on this one, it would shed off, it would spill it. It wouldn't hold the water, it would spill it. Okay. So that's an informal way to think about it. Concave up holds water. Concave down spills water. So a parabola that opens up, concave up, parabola that opens down, concave down. That's that same kind of curvature. And here's a more formal way of thinking about it. So we said the first one's concave upward. If we think about all of the tangent lines we could possibly draw into our curve on the first one, the graph is above all of the tangent lines. Okay. That's concave up. On the second one, if we think about all the tangent lines we could draw in, our graph is below all of the tangent lines we could draw in, so that's concave down. So you say if on an interval a function is above all of its tangents, that's concave up. If it's below all of its tangents, that's concave down. That's nice if you're trying to prove something. To have that more technical definition. Holding water, spilling water, easier to think about usually to me. Okay. So what we want to be able to do is to have some way to analyze what intervals a function will be concave up and on what intervals a function will be concave down. Okay. So where we're headed, let's look at this crazy graph. Okay. It might give me an interval where it would be concave down. A to B. A to B, concave down, spilling water there. Okay. Somebody see another one where it's concave down? C to D. Okay. When there's a little less curvature, it's a little harder to see. So this one's not quite as like extreme as A to B, but it is concave down there. Okay. P to Q, P to Q, yeah. P to Q. Yeah, they're on there. Okay. All right. What about concave up? B to C, yeah, hold the water there. D to E, yeah, D to E. Then one other one. E to P. E to P, concave up. Concave up. Okay, so what's going on there? What's going on there? You can guess it has something to do with the second derivative. Okay. Okay, so on A to B, we're concave down. We've said that. Okay. So think about how the slope of the tangent line is changing over the interval A to B. So here it's positive, and then we're kind of coming a little more horizontal as we get toward the top. So would that mean that our slope's getting bigger or smaller? Smaller. So our slope's positive, but it's smaller positive, smaller positive, smaller positive, and then it's 0, and then our slope is negative from there. So thinking about how the slope of the tangent lines is changing, that's thinking about the second derivative. That's thinking about the second derivative. Okay, so we've got a test we can do. And then let's just look at the test and then we'll talk about why it works. Okay. So here's our test. Okay. It says if our second derivative is positive on an interval, calling it I, then the graph is concave upward on that interval. And if our second derivative is negative on an interval, then our graph is concave downward on that interval. Okay. So let's think about what that means. Okay. If our second derivative is positive, what does that mean about our derivative? Is it getting bigger or smaller? If our second derivative is positive, so a positive rate of change of our derivative, so our derivative is getting bigger. Okay, bigger. And then if we have a negative rate of change of our derivative, then that means our derivative is getting smaller. So if the slope of our tangent line is getting bigger, that means our graph's getting like steeper. And that's concave up. Concave up. If our slopes are getting smaller, okay, then that means, well, let me do it this way. That means we're like smoothing out that way. Okay. So that's concave down. Concave down. A little bit harder to visualize on that one because we've got two layers. Two layers. Let's look back at the picture. Okay. So we start off with, a medium magnitude positive slope. Then it's getting flatter. It's getting smaller. It gets to 0, and then it even gets smaller. It goes off into negative territory. So on that whole interval where our derivative is getting smaller, we'll concave down. Okay. But then we're negative, and we get smaller negative or closer to 0, so that's getting bigger till we get to 0. And then we go positive, so our slopes are getting bigger. Yeah. So that's concave up. So one other definition here. Let me find where it's at. We're skipping over that example for now. Yeah, here we go. Okay. More definition. So the points where our first derivative change sign are local extreme values or local extrema. So they're either a local minimum or a local maximum. Okay. The points where our second derivative changes sign are also important. They're also important. They're what we call inflection points. Inflection points. And geometrically on the graph, visually, what's happening when we switch from concave up to concave down, right, that's when our second derivative changes sign. So an inflection point is where our graph changes from concave up to concave down, or from concave down to concave up. Okay. These are what we call inflection points. Okay. This slide's kind of not great because the second derivative test doesn't have anything to do with inflection points. Okay. So ignore this for this moment. Okay. we're just talking about where our second derivative changes sign. Those are inflection points. Okay. So where our graph switches from concave up to concave down, those are, or from concave down to concave up, those are inflection points. Let's go back to that crazy curve. Okay. All right. So this one's concave down all the way until we get to B, and then it goes from to concave up. So at B, we've got an inflection point. Okay. They're hard to see sometimes if you're just looking at the graph. But right here, our graph changes from concave down to concave up. So that's an inflection point. Okay. Then we're concave up. And then at C, we switch over to concave down. So C is also an inflection point. Okay. An inflection point right there. That one's pretty tricky to see as well. Okay. D stands out. Okay. We're concave down, then concave up, and I mean, that one's pretty easy to see. Okay. Got an inflection point there. Okay. And then we'll go from concave up to what? Concave up. So even though we've got this pointy corner, the inflection doesn't change. I mean, the concavity doesn't change there. Concave up on both sides. So E is not an inflection point. Okay. But then we're concave up and we switch over to concave down, P. So P is an inflection point. Okay. Without being able to do the test, okay, with the second derivative, they're really hard to see. You can sometimes, you can tell about an area where an inflection point is somewhere on the graph. But being able to do the analysis and figure out the exact x value is really helpful. And like, let's look at this example that we're not going to talk much about right now. You can look at this one and tell over in this area, are we concave up or concave down? Concave up, yeah. And then by the time we get to the end, we've flipped over and we're concave down. So somewhere in there, we've got an inflection point because we've switched from concave up to concave down. Exactly what value that's at, it's a little bit hard to see. A little bit hard to see. Somewhere in here. Somewhere in here. But the exact transition value is a little hard to see without doing the actual analysis on the function. Okay. One more thing. That is this last idea here of the second derivative test. Okay. So it can be a little bit confusing. Okay. The concavity depends on the sign of the second derivative. And where the second derivative changes signs, those points are called inflection points. Okay. But the second derivative test doesn't have anything to do with, not directly, with inflection points or concavity. Okay. And the second derivative test is another way for us to find local extreme values. Okay. So the second derivative test serves the same purpose as the first derivative test. Okay. Another method. Okay. So the second derivative test says first, okay, it says suppose the second derivative is continuous near C. Okay. That is not always the case. We could have a first derivative around some value and the second derivative not exist, or the second derivative has some kind of issue. Okay. But if second derivative is continuous around a critical number, okay, and, well, I said it's a critical number already, but if f prime of c is 0, okay, and then our second derivative is positive at c, okay, means we have a local minimum. Or if f prime at c is 0 and our second derivative at c is negative, that means f has a local maximum. Okay. I'm not going to force you into using the second derivative test on any problem, okay, because one thing to take note of, we could add in a part C here. The textbook just talks about it separately, but what's our other option for the second derivative? Could be 0, yeah, if the second derivative at c equals 0, then we don't know anything. That's very informal. Okay, so that's kind of a bummer. At that point, yeah. Yeah, so what this is saying, okay? So let's think back through, like, conceptually what this rule is saying. Okay? This says if our first derivative at c is 0, okay, so what's that mean about our tangent line at c? Horizontal. All right, the horizontal tangent line at 0, you're right. Horizontal tangent line at c. Okay, and then if the second derivative is positive, what's that say about our concavity? Concave up. So it's concave up, and we have a horizontal tangent line. That's when we have a minimum. That's the same thing that we say informally when we say we've got a valley. Okay, concave up, horizontal tangent line. So that's like saying we have a valley there. Okay. On B, if the first derivative at c is 0, horizontal tangent line again. But then if our second derivative is negative, what's that mean about the concavity? Concave down, so that's the same thing as saying we have a hilltop. Okay. So local maximum. Okay. But we could have some different issues where our second derivative could be 0. Maybe it's an inflection point. Okay. So that's a possibility. So it'd be concave up on one side, concave down on the other side. So then does that mean the hill or a valley? We don't know. Or what, it could be concave down on both sides. There's several things weird things that could be going on there. The second derivative test, all in all, if you already have the second derivative for some reason, you're having to do something else with it, second derivative test is fine because it can be really quick. But in general, first derivative test is just more useful overall. Yeah. Okay, there's the notes. Okay. Covers everything we've got to be able to do in this section. Now we just need to do it. Okay, so we had the one example, a little bit increasing, decreasing, but I'll give you several more examples where we go through and analyze the function with all this stuff. Okay, so you can look forward to that. Okay, in the video. Fridays, call it virtual day if you want to. Okay. I'll be in my office if you need to come by for any reason during class time on Friday. Amen. If you don't need me on Friday, then just look forward to the example videos we got coming.
What time will we do?
maybe post it like during like class?
The video.
Yeah, or it can just be anytime.
Yeah, it'll just be any time before we get back. I'm gonna kind of see how my voice is doing. It's doing good right now. Yeah. Hopefully it's getting better, but this morning was rough. Stop the video here.